It is my pleasure to introduce our four distinguished speakers this morning. We have first Hans Gougar. He is, as you can see, the Director of Advanced Reactor Technologies Development at the Idaho National Labs. After that, we have Rizwan Uddin, who you've already seen, and I am personally grateful that he is now the Director of the Illinois College of Engineering Initiative on Energy and Sustainability Engineering here at the University of Illinois, as well as his role in the organization that's sponsoring this conference. After that, we have Martin Freer. He is Director of the Birmingham Institute for Energy and also head of the Physics and Astronomy departments there. And finally, James Stubbins, the Willet Professor and head of the Nuclear, Plasma, and Radiological Engineering Department at the University of Illinois. As you heard from Steve Koonin, our keynote speaker, nuclear energy has the potential to make major contributions to the transition to a low-carbon future. And one of the reasons for that is that nuclear energy remains, with current technology, the least expensive way of providing baseload power. Along with the advances in transportation without internal combustion engines that we've heard at this conference, nuclear energy has the potential to provide perhaps half as much, half of the total energy in a low-carbon energy economy. However, there are three serious complications in the way of that possible future. One is cost. Currently, under competitive market conditions, new nuclear reactor builds are not competitive in any place where there is both large amounts of conventional or shale natural gas that is competitively can be extracted. And in states like Illinois and California that have renewable energy mandates that do not include nuclear energy, even existing reactors where the capital cost of the reactor has already been paid off are in some cases not commercially competitive. The second problem is the disposal of the high-level waste that comes from nuclear reactors. Only two countries actually have in progress, as two small countries have in progress actual builds of such depositories. And again, in Illinois and California, there is legislation against the construction of any new nuclear reactors until there's a solution to the high-level waste problem. The third problem is, the third complication has to do with the potential for military uses of both uranium enrichment and the plutonium that nuclear reactors produce. In some countries, Germany comes to mind, this connection between the military and civilian sectors has produced a serious public reaction against nuclear energy. And in other countries, some in the Middle East come to mind, which have vast supplies of natural gas nearby. The pursuit of the build of nuclear reactors that would not otherwise be commercially competitive has been pursued. So I hope that our four speakers will shed some light on how these complications will interact with the future of nuclear energy in a transition to a low-carbon economy. So let's start with Hans Gougar.
Thank you, Professor Singer, and thank you for inviting me to this conference. It's the first sustainability event that I've attended in my career, and I wasn't sure exactly what to expect or what kind of audience I would be addressing, and I'm still not quite sure, so have your tomatoes ready. Oddly, this is also my first trip to the University of Illinois, despite having spent my early childhood just right up the road in Joliet, and having gone to a Big Ten school that shall remain nameless. This is my first trip here, and I'm glad to be here. Thank you. All right, so I've got 20 minutes, and I've got a lot of information on these slides. Too much for 20 minutes. I'm just going to try to hit the highlights, and hopefully you'll see something in there that will intrigue you or irritate you or say, I don't think that's right, and you'll go and investigate it on your own. And if you certainly find something that you find controversial, do send me a note and we can have a discussion offline. So first of all, since it is a sustainability conference, I decided, okay, well, is nuclear power sustainable? And I had to first figure out what that really meant. So I did like any normal person, I Googled sustainability and I tried to gear the first part of that, my talk toward that issue. And then I want to get into the discussion of advanced reactor concepts. That has been my life's work for the past 15 years or so, very dear to my heart. And then why are we not building these new advanced reactors currently? Okay, first, this is an interesting one. This is how we make and use energy, put out by my colleagues at Lawrence Livermore National Laboratory. And you'll see in that slide, it's very complex. I'll just show the highlights. On the left are the sources, primary fuels used to power our industrial economy, fossil fuels, nuclear, renewables, etc. And you can see if you follow the lines, which are the width of which indicates the contribution they make, that about 38% goes into making electricity. It's converted into electricity, therefore it can be transmitted easily to power whatever it's useful for it. The rest, and mostly comprised of fossil fuels, is direct combustion in transportation, in cars, and in furnaces to heat your home in the winter, and so on. So if you're just thinking of sustainability and carbon-free energy, if you're just looking at electricity production, you're only getting about 38 to 40% of the picture here. You need to look at the whole thing. I'm sure I don't have to remind most of you of that. Nuclear power only contributes to that 38% that is converted to electricity. We are pondering ways to expand that to make nuclear power useful for making other types of transportation fuel and so on, but right now we just push electrons, so to speak, we being the nuclear industry. How long can we last at the current rates of consumption of known deposits of uranium? Well, if we take pre-Fukushima numbers back when Japan was running all of its 30 or so, 38 reactors, given the known reserves, this is uranium that we know is in the ground, we can dig it out or use other means to take it out and then and convert it into nuclear fuel. At the rate we were burn it, it would last us another 82 years, give or take. If we have different growth scenarios in nuclear, high, low, et cetera, maybe that would either shorten or lengthen depending on how many reactors we build and so on. But that's just with known reserves. Of course, known reserves of petroleum were estimated to run out by the year 2000 as recently as 30 years ago. We had reached peak oil and we're going to run out of oil, we'll have to go to something else. But of course we found other sources of petroleum, and natural gas seems to be a glut on the market these days. And no doubt if we look harder for uranium, we will find it, and there's some footnotes down there you can read. If we use uranium that's dissolved in seawater, for example, and extract it, then we can last for hundreds of years with the way we burn uranium today. And by that I mean the so-called once fuel runs through fuel cycle. A nuclear pellet has a rough shape there up under where it says fresh fuel. It consists of about 3% of the uranium-235 isotope, which is directly fissionable by thermal neutrons in a reactor. The rest of it, the vast majority, is uranium-238, does not fission, and it just becomes part of the spent fuel that is put in a repository or stored on site. We know we have the technology to convert that uranium-238 into a fissionable material, plutonium, and then burn it. So we can conceivably burn the entire 100% of that pellet. And if we do that, then known uranium reserves, and if you throw in thorium as well, which is even more abundant than uranium, then we can fission reactors and make electricity for literally thousands and thousands of years at any consumption rate. Doing that, recycling fuel, is not a straightforward, inexpensive option. To recycle fuel and burn it in special types of reactors like this would require more engineering. We know how to do it. We've built reactors that do it, but it's not cost effective today in the energy marketplace. There are other impacts of interest. What does nuclear power do in terms of the natural resources used to build and operate those plants? And here I've relied on some information from the Breakthrough Institute, which is not aligned with the nuclear industry, but takes a particular interest in energy issues. You can go to their website and pull up this report yourself, check its assumptions and conclusions, et cetera. But I wanted to look at land use, concrete use, because there's a tremendous amount of concrete used in reactor buildings. Steel, a lot of steel used in these plants. And also there's a slide on there showing the reliability, the capacity factor, what fraction of the time is that plant up and operating or generating power. You can see from there that the renewables, geothermal, wind, solar, et cetera, have very low resource requirements in terms of land, concrete, and steel. For the most part, photovoltaic is actually uses up quite a bit of land, takes it out of use. Same with concentrated solar power on a per gigawatt year basis, amount of energy produced. Nuclear is very low, even compared to the traditional renewables. Steel, concrete, you name it. Have you never taken it? We've got, where I live in Idaho Falls, we've got a very large wind farm just east of town. And all you can see these beautiful, and I'm not offended by the way they look. I think they are kind of neat looking machines. But if you dig down in the ground underneath each one of those windmill pylons, there's a tremendous amount of concrete that's used to keep that thing from falling over and reinforced with steel. So this is where those numbers come from. Here's an interesting one, life cycle emissions of carbon dioxide equivalent. So if you account for construction, fuel, mining, transport, operation, decommissioning, and waste disposal over the lifetime of the facility, you can compare in CO2 equivalent because, for example, making concrete releases a lot of carbon dioxide. Processing the steel, making the steel, transporting all the equipment to where you want to build the plant, et cetera, all produce carbon. So this chart looks at the life cycle emissions of carbon of what the major energy supplies. Forgive me that biofuels isn't on here. Nuclear is right down there in the noise with the traditional renewables in terms of carbon emission, equivalent carbon emissions, and then you get into to the fossil fuels, and you go up quite a bit up the scale. But nuclear is even lower than on an absolute number basis than just about any other electricity source. Nuclear does consume a lot of water, and I put that in quotes because to cool these reactors requires a tremendous amount of water. They suck the water in from a river, they run it through some heat exchanger, and pull off the heat out of the power conversion system and send it back to the river in a slightly warmer condition, which may be good or bad for the local ecology of that river if you don't control it properly. Sometimes it leads to great fishing, but you got to have it under control. If you're not putting it back into the river, you can use it to make steam. The traditional cooling towers, the steam is coming up, and that water comes out of the river or the ocean and then floats away and rains on somebody else's parade. So it doesn't actually consume water, a nuclear plant does. It's just used to cool it, and then you take it out of the local environment and you put it back somewhere else, either in a different state or in a different location. But nonetheless, it requires a lot of water to cool these plants. So that was just my first introduction. You know, what does nuclear look like compared to other forms of energy in terms of resource consumption and the ability to supply energy for a long period of time? And nuclear actually holds up pretty well. Now I want to look at nuclear power, how it's evolving, and in some cases you can say it's not evolving. We're still running the same types of power plants and the same technology that we developed back in the 60s and 70s. This is called Generation 1. Generation 2 power plants are the ones that supply 20% of our electricity today. We are looking at newer designs, evolutionary designs. 4 of them are being built in the eastern United States right now, but they're still basic light water technologies, like going from a rotary dial telephone to a push button telephone. we're not quite making the leap to a cell phone yet or a smartphone in terms of a nuclear power equivalent. Those cell phone equivalents of nuclear power plants are what we call Gen 4, and this is what we work on at the Idaho National Lab. We'll talk about those a little bit more. The Generation 4 mission is to design and build reactors and deploy reactors that are better at resource management and getting more electricity out of the uranium they burn. They're supposed to be cheaper than today's power plants. Less opportunity for Fukushima-like core damage, and then finally less resistant to a proliferation of weapons material. That's the Gen 4 mission. There are 6 Generation 4 reactor concepts that are being investigated around the world today. About 10 or 11 different countries, including the US, are members of what's called the Generation 4 International Forum, where they coordinate and share research and development of one or more of these types. The US focuses on those first two, the very high temperature reactor and the sodium-cooled fast reactor as options that we find most promising. I'll let you, you can just Google Generation 4 and you can find more about these different systems, how they're different from today's reactors. Now, I'm running out of my time, so I want to talk a little bit about why is it that we're still using reactors that we built 40 years ago? Why do they look the same? Even the Generation 3+ reactors that we're building in South Carolina and Georgia look a lot like and behave a lot like the reactors that we've always built. When indeed Apple comes out with a new iPhone every year, Toyota makes tweaks their Prius design every year and rolls it out, and they can sell it. There are a number of reasons for this. Mainly, and Professor Singer addressed some of them in his opening remarks, but nuclear reactor construction and the way we design and approve nuclear reactors is a little bit different. All systems, structures and components, fuels, materials, analytical models must be qualified for use under anticipated chemical, thermofluidic, and neutronic conditions before the Nuclear Regulatory Commission will allow you to deploy it in a new system or even backfitting an old system. Each one of these changes that you make, maybe you want to switch out an old valve that was put in there when the plant was built with a new type of valve, which may be better, more efficient, more effective at doing its job. You have to show the NRC that a standard exists that says that's okay to put that valve into the reactor. The presumption is, if I may be so bold, that if there's not a standard associated with it, the NRC won't allow you to put it in there. And if you try to put it in there, that means you're threatening the safety of the plant and the public. So reactor vendors go through a lot of analysis to decide, is it worth the investment to upgrade that valve or upgrade that design or make a new fuel element or change this or change that, because it's going to take me years to qualify that through one of these many standards agencies that says it's okay to put this component, to make this change to my plant to make it run better. And quite often it's just not worth the effort. It takes years and years of experimentation and paperwork and convincing the NRC that you've got it, you've done it right, and you've done your homework, and this change makes this a better plant. It's not a simple process to go through. It's very expensive, time-consuming, labor-intensive, and there's no guarantee at the end that the NRC will say, okay. It's a little bit tenuous, and certainly investors out there that are paying billions for this plant or have billions to pay for this plant are thinking, I don't know if I want to do that. I just can't see the return on the investment. If you look at what we call a path to deployment of a new type of reactor, even if it's just an evolutionary change to the reactor, it looks something like this. There's a lot of research and development. Then you have to do some sort of engineering demonstration. Then there's a performance demonstration. Yeah, we know that it works, but can it make money? Can it do as we expect it to, can it perform as we expect it to? And then finally, yes, if we've overcome that hurdle, then we have to go out in the marketplace and compete against $3 natural gas, cheap oil, and wind turbines. That cost, that path to deployment, you can see on the left, I'm measuring it in billions of dollars. And it'll take you, right now, it takes about $10 billion to take a new plant online. Now, if you spread the cost over the life of the plant, considering that nuclear fuel is so cheap and operating is relatively cheap, then yes, it is you can make money off of that proposition. But you still have to go through that approval process from the NRC, and there is no guarantee that you'll pass through that approval process. And so therefore, a lot of venture capitalists, with a few notable exceptions like Bill Gates, are willing to put in those billions to do the R&D, to do an engineering demonstration. Bill Gates and company don't think they can build their engineering demo here in the US. They're talking with China. It's a little bit easier to build a new type of reactor plant in China because the approval process is less onerous. Then they would say, okay, we got it built over there, let's come back and sell it in the US or whoever wants to buy it. But still, we're talking billions and billions of dollars and a long 20-year deployment time. Investors don't like to hear those words. They don't like billions. They don't like decades. They want shorter, lower numbers. Can we speed up deployment? Well, of course, you can just try to speed it up by putting more money into qualification of new plant designs and new components. I put this one in a level playing field. Right now, a lot of renewable portfolio standards don't acknowledge the low carbon benefits of nuclear power. So there's less of a return on the investment there, less likelihood that the state will allow them to build a plant. Licensing. Let's get the technology neutral licensing. And many of the regulations on the books today for nuclear power plants are specific to light water reactors. You have to, for my nuclear colleagues know, you have to watch your critical heat flux and that kind of thing. That's not applicable to the new designs that we're working on today. There's no water in them to boil and therefore lead to a meltdown. So let's get away from some of the regulations that are kind of in the way and not providing any benefit. Bounded, phased licensing pathways that recognize inherent safety features, allow for experimentation and innovation. Say, maybe we don't have to have a standard with 100% certainty that it'll work. Maybe we can get away with 50% and let you experiment a little bit because we know you're not going to melt this thing down and destroy the countryside. We've had 4 meltdowns in history, 4 severe core damage reactor incidents. And the releases, in each case, the containment system did its job and kept radiological releases to a minimum, and no one was hurt from the radiation. A lot of stress involved, dislocation and all that, certainly, but not from the radiation. Modular construction techniques, additive manufacturing, these are all innovations that have been applied to other industries that we would like to try out in nuclear as well. We think that would help bring the cost down. Science and engineering to identify design candidate materials like is done here at the University of Illinois Department. These things can help in the long-term technical prospects for the technology. Okay, that was a brief overview of what I want to talk about. Is it sustainable? Yes. Is it expensive to innovate and deploy a new concept? Very much so. And we have to look at, there are good designs and ideas out there for reactors that are much possibly better than in different ways than the reactors we have now, which are pretty good. We have to find a different way to get from where we are now to where we want to be. Thank you very much.
Okay, so on to the second talk. And so I'm Rizwan Uddin, as you can see. As you cannot see. Okay, now you can. I had to think a little bit about, what to talk about, so that is not going to be repetitive. So I based it basically on my recent experience at the University of Indiana, where they had a sustainability workshop, and I was the nuclear representative, and it was a very interesting discussion, okay? Because it was not just talking to other nuclear engineers or just talking to other engineers. There were people who we really need to convince them that nuclear power is how to compare nuclear power with other sources of energy. So the real title for my talk would be more appropriate if we called it, and the emphasis should be on quantitative comparison of energy sources for their life cycle impact. So my focus is now going to be so why do it? This will be focused on only comparison between fossils and nuclear at this point. There are brief references to renewables, but as you can see, that these are not going away. That is the main point to begin with, to make sure that this is the reason why they both need to be looked at more carefully. That is because the fossils are not going away, and nuclear is definitely also not going away, at least not in China, in many other parts of the world. Okay, so there have been various discussions. Here's a letter from earlier February 2016 from Secretary Moniz. This is a charge to the coal group and asking them to come up with technology for carbon utilization. So CCU, CCUS, CCS. So we've been talking about that, and this is 2016. So this is based on recognition that actually coal is going to be around, at least for some foreseeable future, and hence we need to develop technologies to do something about the CO2. Okay, so this is the report that came out from. This is in draft form, still not the final version. This is from the coal group, and so they are working on the utilization of CO2 to make coal more acceptable. Okay, the executive summary of that. I don't know how much you can read. I suppose only if you focus on the underlying parts. So carbon capture, utilization, and storage is going to be needed. They have to be deployed to achieve climate objectives in the U.S. So this is something that will be worked on. Fossil, including all the three, will remain the dominant global energy source in the future. CO2 utilization can help to reduce cost, etc. Okay, nuclear. Nuclear has shown its own resiliency. If you remember from the 80s and 90s, it looked like it had died. And then all of a sudden, there was a huge upsurge and renaissance, as we call it, until about 2011. And then, had it not been for Fukushima, to some extent, and mostly because of shale gas, that we have inched away, although some other countries like China, etc., they are still moving in that direction. So if you look at, for example, as evidence for that, this is the student number, enrollment number in the NPRE department, Nuclear Plasma Radiological Engineering department on campus. This unfortunately only goes back to 2005, 2006. If you went back to 1996 and 1998, the undergraduate numbers were down to about 40 to 50. Okay, and then we increased from there. We went to more than 200 undergraduates in the program, and now we are stabilizing at about 150, 160. So that shows, in some sense, the confidence in the nuclear, the up and down, and the acceptability of nuclear power. Here is an article, and this is from July of 2016. Of course, U.S. News and World Report, but the key point here is who are the authors. These four names, if you recognize, these are four senators from the U.S. Senate. Okay, and they were willing to write an article with such kind of a title, and they are putting their money, or I don't know how it works with money. They don't put money; they actually usually get money. But so this is so both are likely to be around for some time. So the question is, how do we make decisions? And this is where that discussion in Indiana came up. That it was like talking, past. Other people that who did not know your premise, you did not know their premise. So usually it comes down to that you are comparing apples and oranges, and hence it's very difficult. But we have to come up with something, if we are forced to do this, If we are forced to make that comparison, how do we do this? Okay, there are plenty of qualitative. I will quickly go through these things because if you start looking, there are many qualitative comparisons that are available. I mean, people say this is good because of that, because of this, because of that, but concrete numbers like the ones that Dr. Gougar showed about, concrete use, concrete numbers about concrete use and steel use and other things. So they are much more useful, but there's more needed because the public is concerned about other things. They're not really concerned about how much concrete one technology is using against the other. So, for example, just taking some examples from the renewable side also, people are sometimes worried about the visual impact of windmills. And if you look at even the concerned scientist website, they do talk about the downsides of different renewable energies. And how much land they use, what will be the impact on birds' migration routes and so on. But the point is that these are all qualitative. You can see there's a pros column and there's a cons column. Okay, how do you compare these things? What we need is a methodology for quantitative comparison. And this is going to be the gist of the talk, that what we need is an evaluation of cost and risks in some very quantitative fashion associated with different energy sources and the associated technologies. And the challenge becomes the scale that you see on the lower left there, that you have to compare when you're talking about carbon or when you're talking about accidents, nuclear accidents. The scale is global. Okay, so you have to compare values. We heard about values yesterday. Values that will exist in today's developing world versus values that exist in developed worlds. Okay, you have to somehow adjust those. Same thing. Same question about time. The timeline. So the right one. This is just to show you what kind of timeline can become important. But here's the timeline for nuclear side. Okay, the waste. Look at the x-axis, and that's goes up in this log scale. Time after discharge, we are talking about tens of thousands to hundreds of thousands of years. So that makes the problem very challenging. Okay, the fossil side, same thing is true actually, but not maybe as much realized by the general public. Okay, what is a gigaton of CO2 doing to us today that is already out there versus 2 kilograms of very highly radioactive substance, which is at least contained somewhere. So here's the website, Physicians for Social Responsibility. They are affiliated with a group that actually got the Nobel Peace Prize in 1985. And their website says dirty, dangerous, and expensive, the truth about nuclear power. So this is what we, the nuclear engineers and others who think that nuclear is a good option, need to counter in some ways. Okay, if you look at the third line that is underlined, they're talking about their radioactive waste created during the nuclear fuel process, including 2,000 metric tons of high-level radioactive waste. Okay, 2,000 metric tons. Okay, you need to put that in perspective. I guess people here who are worried about carbon dioxide, they know what kind of units we use, what kind of 10 to the power n we use when we talk about CO2 emission. It's in gigatons. Okay, and it's already out there. Oops, that's not what I wanted to do. Okay, so cost and risk associated, again, still from the same website, that the language is fine, for lay public, but there is no quantitative comparison with the options. So what do they say about the option? When the very serious risk, so this is one final sort of comment, when the very serious risk of accident, proliferation, terrorism, and nuclear war are considered, nuclear is a bad investment. Sorry, I need to, there was another. Okay, yeah, this is the one that I want to point out, making the safe, sustainable investment, as if it was that easy. It is clear that alternatives to fossil fuels must be developed on a large scale. Okay, so it is not that easy. I mean, my initial point was that we are not going to get away from fossil at this point. Okay, and I think most of us will agree. So it is until that happens, the choice in some sense is going to be between nuclear and fossils. Okay, so here is after 5 years, what's the cost of Fukushima? This is from Forbes magazine. So despite some neutrality in there, actually, the article sort of favors. It's in favor of nuclear power. It talks about Fukushima. What is the cost there? So up here they will show $15 billion in cleanup cost. Replacing Japan's 300 billion kilowatt hours of nuclear energy that was coming from nuclear is going to cost Japan $200 billion. Okay, the cost will double. And in many other places, you will see the pro-nuclear tilt of this article versus the sort of very anti-nuclear tilt in the previous website that I mentioned. The challenge is, how do we, as scientists, we put them, and scientists and engineers, how do we put them on a quantitative scale and make that comparison? Okay, so more and more of sort of indication. The language is very clear that this article is supporting nuclear power. It is indicating, how bad it has been for Japan by, because of the fact that they shut the reactors down. Here's something from CNN. Okay. Air pollution cuts life expectancy by 5.5 years in China, in some part of China. Is it reliable? Should we believe it? And if we do believe it, and if it's not 5.5 years, if it is 1.5 years, I think this will be a huge argument if it can be put in quantitative terms, solidly backed in the debate between fossil and nuclear. Okay. The IUCN people, they recently had their conference ended from, it was from September 1 to September 10th, came out very strongly, against well, not directly CO2, but they are worried about climate and the changes in temperature that is taking place in the CO2. Reported in Guardian, actually, if you look at this is somewhat quantitative, but it shows on a scale the temperature anomaly, and it shows the numbers actually vary from 1980 to 2015. It just shows very clearly how 2016 has been so different from other years over the last 25 years, 35 years from 1980. Significantly different. And what will be the impact of something like this, the top curve, the solid curve, which is 2016, can have catastrophic effects. Okay, so here's another way of doing the comparison. You remember the 2,000 metric tons and the 58,000 metric tons of waste that has been accumulated since in the U.S. since the beginning of the nuclear era. Here is something that I get it in my electric bill every month, a statement every month or every year, a statement that shows for every 1,000 kilowatt hours of energy that I use, what was the source of energy, okay? The column that shows 50% came from coal, 16% came from nuclear, 20% came from gas, and so on. This is the source of energy. And it also shows me this, okay? What came out of this? For every 1,000 kilowatt hours, this is 2015, for the sources used in 2015, carbon dioxide, 1,300 pounds, nitrogen dioxide, sulfur dioxide, and look at high-level nuclear waste and the low-level nuclear waste, okay? And if that helps, the high-level nuclear waste and the low-level nuclear waste is contained, it is under our control. The CO2 is not. CO2 is out there already, doing what it is supposed to do, heating us up. And if you look at this underlined line there, CO2 is a greenhouse gas, in quotes, which may is the key word, right? May contribute to global climate change. So this was the website, where they quoted 2,000 metric tons and the 58,000 metric tons of highly radioactive waste. That is So there are two ways of presenting this information. The important thing is to do this in a comparative fashion. In a comparative fashion that actually makes sense and is backed. So from 5.5 years of life expectancy loss, which one would I take? Which one would you take? Versus the possibility of a catastrophe happening, which might, release radiation. Okay, put a dollar amount. Chernobyl accident, Fukushima, 1 degree rise in temperature, sea level rise. Okay, so there have been some studies. So if there's a half a meter rise in water level, what is the cost to the world? If there's 1 meter rise in water levels, et cetera, et cetera. So what are those numbers? Of course, some things are in hand, others are prediction for the future. But a real disastrous nuclear accident is also a prediction for the future. There's a probability associated with it. And so the comparison has to be done, including what will be the top thing is risk analysis. Okay, so this is going to be the bottom line, that this is what is needed. Okay, a lot of pieces are there, but what we need is a comprehensive study where we put together a model in which there will be plenty of knobs and parameters that we will be playing with. Okay, different people will want to put different number on those parameters because of the value system that we have. Okay, a developing world person might say, no, this should be 0.1. The developed world person might say, no, this parameter should be 0.9. Okay, and similarly, even within a particular society, different people may have some arguments about, and that's where the debate will shift. What should those numbers be? But at least a very comprehensive, integrated model is needed, which will take all of these things into account. Risk analysis, uncertainty quantification, we talked about that yesterday a little bit, or day before. Steve Koonin talked about it first. And the economic analysis, of course, that those models will be the social science to associate cost of disruptions in life. But the other question will be, how do you want to compare? In the end, if there's going to be a metric, what is going to be that metric? Is it going to be a dollar figure? Is it going to be a loss of life? How many days you will live less if this is the source of energy versus the other one, and so on. Okay, incorporate flexibility to include different value system, impact on current, future, etc. Thank you. I don't know. I can close it.
So good morning, ladies and gentlemen, and thank you very much for coming along at such an early hour. Thank you also to the organisers. This has been an intellectually stimulating conference, workshop. So hey, I've learnt many things. I've also, and thank you for this, changed my mind on many things. When I go to conferences like this, I find them in some ways enormously depressing as well. Depressing because no matter what we do, there's a lot of people in this room pedaling very fast and very hard to change things. And there is a sense that we are all in a supertanker, which will take a lot of turning around. And actually, even with the kind of investment that Mike was talking about in his talk, billions of pounds invested, my sense is that even that may not be enough. And I tend to agree that with Steve Koonin that mitigation might be the right approach, and that the academic community might not be enough in terms of delivering the kind of change that is required. Never mind. So I go away slightly more depressed than when I arrived. Let me tell you a story, which is in some way connected with Daniel's recommendation to us, and Daniel has he Ubered himself out of here. So Daniel last night told us that we should look up from our desks and our computers and go out and engage with the real world. Now, but I'm going to tell you a story about what happened in the UK. Now, you might not care about the UK, but in the context of what you're trying to do here for the US, you might learn some things about what we've done in terms of our story. So this is a picture of my university, University of Birmingham here. And what I did back in 2012 is worked with Lord Hunt. Now, Lord Hunt had been in the Labour administration, so Labour means Democrat in your terms. He'd had a lead for energy within the UK, and under his administration, the UK, back in about 2007, said, we've got to do nuclear power. And actually, at that time, that was a really brave thing to say. A lot of people were very strongly against nuclear. So I worked with Lord Hunt to try and figure out what the solution should be in a UK context. And this was looking at everything. It was looking at technology. It was looking at what we might do in the future in terms of Generation 4. Should we be thinking about thorium as a fuel? What on earth are we going to do as a country in terms of that waste disposal? What about public opinion? What do people care about? What are the arguments and how should they be made? Now, before we kind of explore some of that thinking, in order that you get the context and where on earth the UK is and how it's trying to fix its energy challenge, take a look at this. So this shows us how we have marched on in terms of our mix as a function of time. What you'll see is back in the 70s, we had a coal-dominated economy. And as we got to the mid-90s, we developed our own resources of gas, and so gas became very important. And in 1993, we built our last nuclear power station. And so you can see a small increase in nuclear power. UK's got a very long heritage in nuclear power. It goes back to the 1950s. It stops at 2008. But you can see that the message there is that if the UK is going to decarbonize, well, it's a big challenge because you've got to get rid of all of that coal and all of that gas. What does it look like in almost now? This is 2014. The really great thing, and I guess you can do this in the US as well, you can minute by minute look at how we're generating our electricity. These are two snapshots taken over a 24-hour period in January and September. So there's some obvious things. So in January, you need more power. We use electricity for heating. You can see the mix and how it varies from night to day. You can see that what we're doing is we're using gas, by and large, to control the variability. Nuclear, at the moment, is about 20%. And you can see nuclear power, it has its problems, which is that it is base load, and so it just chugs along, producing that 20% of nuclear energy. Wind, we've done a lot. We've installed quite a lot of capacity now, somewhere close to 20% renewables. Here you can compare and contrast one day when there was a lot of wind and another day when there was no wind, and you can see that demand switches over to gas. And as we try and shape what we're doing in terms of the future, there are some pressures. So the UK was very brave, or alternatively incredibly stupid, in the sense that we committed ourselves through a government act, the Climate Change Act, to reducing greenhouse gas emissions by 80% compared to 1990 levels, so times of the Kyoto Agreement, by 2050. So we're legally obliged to do that, and you can imagine the challenges that come with that. We need to think about a sustainable and secure source of energy as we go forward in the future. So we do have our own reserves. So the graph, the chart shows the North Sea oil and gas production, so something which actually fueled the UK economy for a while. But you can see that those reserves are beginning to taper away, and exactly when they extinguish is not clear, but maybe 2030, 2040, they're gone. So we need to think about security. We're an island. And, you know, I've been waiting many years to present this graph chart in the US, and so finally I have a chance to share this one with you. It comes from a great book, and if you haven't had a chance to read this book, it's well worth a read. It's by David McKay. He was Chief Scientific Advisor for our Department of Energy and Climate Change. Get that, we had, it got abolished just. We had a department, a government department for energy and climate change. Anyway, he was the Chief Scientific Advisor, and he wrote this book to get the public to try and understand how you deal with the challenges around energy. Fantastic. So anyway, here's his graph. Now what's plotted here, every dot is a country. What's plotted on the horizontal axis is population density in some units. And on the vertical axis is power consumption per person in some appropriate units. Now, what you're desperate to know is where is the world average and where is the European average? Okay, and you can see the world average is here, the European average is slightly higher in terms of consumption, as you would expect. Now, the reason I've been waiting all these years to share this is because here is the US, and here's a moment for you to be embarrassed as a country. So that your power consumption per person is extraordinarily high. Let me share a fact with you, that you, as a country, use more electricity on air conditioning than Africa uses on everything. You could just turn, I'm sitting over there feeling absolutely frozen most of the time. Where is the United Kingdom? Well, we sit over here, and is that good or bad? And what this chart helps you with is planning what your energy strategy should be. Because you might have noticed there's some diagonal lines here, and those diagonal lines tell you how much power per meter square of land of your country you need to generate. So if you're in the bottom left-hand corner, you can see it's a milliwatt per meter squared, and you will see actually there's not too many countries down there. If you're in the top right-hand corner, well, I can't read it, but from memory Kuwait or somewhere's up there, that's a bad place to be because you need to generate a lot of power and you've got only a small amount of land mass. What about the UK? So UK, you can see, sits on a bar which is just over 1 watt per meter squared, so 1 or 2 watts per meter squared. It's a logarithmic scale. And you'll see on the right-hand side a whole bunch of energy generation technologies. And if you were to take, for example, wind power, which can deliver something like 2 to 3 watts per meter squared, for the UK, that's what a wind-driven solution would look like. And there's believe me, not many people who want to vote for that. So the UK has been moving its energy-generating technology from wind offshore, and actually there's some very large installed wind power capability offshore now, and we're leading in that regard. So good, and that's how we've got up to such a high fraction of renewables. But that's only 20-odd%. So how on earth do we get this delivery against our Climate Change Act? So here's another innovation which I think is very good, very powerful. We have an independent committee, so this is a committee on climate change, and their job is to provide advice, independent advice to government on how they are going to make or achieve their carbon targets. So this was a report written back in, as you can see, 2011, and this is one of their scenarios. How do we do it? So their suggestion is you go hell for leather. You build as much renewables as you can. So given how much manufacturing capability and capacity there is, and they estimated you could get to about 40%. We could probably put up with 20% of gas. And in this calculation, they were relying on carbon capture and storage. which in the UK context has had some challenges recently. Then that leaves a gap of about 40%. So in a UK context, the only way, realistically, you can fill that gap is with nuclear power. And why? So this is not a bunch of people who are really keen about nuclear power. They're pragmatists. They are looking to see how we can solve the climate change problem. So of course they, and you've seen this already, they looked at what is low carbon, and you see nuclear vanishes off the scale compared to other technologies. We now have legislation which says you cannot build a power station which gives you more than 400 grams per kilowatt hour. So coal now is no longer happening in the UK, and coal is disappearing off the grid faster than you can imagine. So how does it compare if you blow it up? Well, actually it's very, very close to wind. And that calculation, the one that's shown there, is for a particular reactor. It's an AGR reactor in Torness, so a British reactor. And it's a whole life cycle analysis in terms of the carbon emissions. So what have we got in terms of nuclear power in the UK? Well, as I said, we've got 50 years of doing this, so we've got pretty much everything. We have some reactor designs called Magnox reactors. The last one of those was in North Wales, so if you know what your British geography. It's right at the top there on Anglesey. So that one came off the grid recently. We have a large number of gas-cooled reactors, AGR reactors, and we have one pressurized water reactor over at Sizewell over here. So we've got a mix of technologies, but it's all aging. So what's happening in the UK, just at the point where we need 40% nuclear power, we're doing this. This shows how much generating capacity we have as a function of time, and each of those names there corresponds to a reactor, and gradually it's all been switched off, and by some 15 years so we will have only one operating reactor, and that will be the PWR Sizewell B. We have been through a life extension program, so some of those AGRs, working with universities, working with the regulator, now are certified to work for a little bit longer, 2023, but that's not changing things. So we need nuclear power. We're turning off our nuclear power stations. Seems to be a bit of a contradiction there. So what's happening? When I was wringing our hands in misery, we have a program of building more nuclear power stations in the UK. So the government, incentivized by the Committee on Climate Change, have gone out and said, come to Britain and build your nuclear power stations in Britain. So the first one is called Hinkley Point C. You'll see a picture of it here. It's not a real one yet. It is a massive plant. It's 3.2 gigawatts. It will operate, so that's about, it says 5% there, but it's actually about 7% of UK electricity in one power plant. That's astonishing. It will operate for 60 years. It used to cost, when I first started this, £6 billion, and now it's been through the regulator and all sorts of other constraints. It's now up to a price tag of, get this, £18 billion. Okay, you told us 10 billion, I can beat you. So what does it look like? So it's a pressurized water reactor. It's not so dissimilar to what has been built in France already. It comes from Areva. EDF are the utility in the UK. It's actually very close to the one that we're operating right now, Sizewell B, but it's been through several iterations, so it's slightly more complicated. It is being built in countries like Finland, and it's being built also in countries such as China. So in Taishan in China, there are a couple of EPR reactors being built right now. Actually, it's an interesting model. 70% of that project is owned by the Chinese, only 30% by the French. It's been through the UK regulatory process. They like it. It's a safe reactor. It's improved safety. It has this fantastic double skin. It is designed such that if you were crazy enough to fly a 747 into it, the 747 should just bounce off. It has, and there's many new reactor technologies. This is actually the AP1000, the Westinghouse design. This has been greatly improved in terms of simplifying the internal structure, reducing number of components, use of passive safety. Again, this is a reactor which has been through the British regulatory process. And in the case of the EPR, its safety comes from having many backup systems of very similar design. Cost. Cliff, you have to tell me to shut up at some point because I didn't even look at the time. Oh, I can keep going. All right. So cost. So there is a constant criticism that nuclear power is too expensive. And what this is, again, it's an independent analysis by that Committee of Climate Change, on what different technologies have in terms of their cost. And you will see nuclear is this bar here, and that price point there is set. The conversion at the moment is 1.3 pounds per dollar. It's set as 92.5 pence per megawatt hour. Coal is, gas is over here. We've got onshore and we've got offshore wind, and various other technologies. So it's reasonably high compared to gas, and in fact this is slightly dated, so gas prices are now a lot lower. What does it look like in the future? So it's reasonably competitive, but if you get beyond the first-of-a-kind costs, which are really, really high, as we've just seen, and you build many reactors, so the prediction here is that actually that cost will come down. And if you do have a proper price for carbon, you will notice that the gas price has gone up. And with a proper price of carbon, you'll see that actually in this analysis, nuclear is very, very competitive. So is it just EDF? No. We have the Japanese coming to town. So through GE Hitachi, we have the advanced boiling water reactor being built in the UK. So that actually will go into that North Wales site, replacing that Magnox reactor. So already they are developing those plans. And believe it or not, we have the Chinese coming. So two companies, so CGN is the one that collaborated with EDF around the construction in Taishan. They are working with another company, CNNC, developing a reactor design. It will either be this one, so the ACC 1000, or the HPR 1000. So a couple of designs which will come to the UK. So the Chinese, and you're probably thinking, well, what do the Chinese know about nuclear power? And you can see actually they've been doing it since the 1980s. So they know, believe me, a hell of a lot, and they will be world leaders before we know it. So there is, don't be complacent. Anyway, the Chinese are coming. And even through another company, Toshiba, New Gen, and we will get the AP1000s coming to the UK as well. And you're going, well, why on earth? Why on earth are all these companies desperate to come to the UK to build their reactor technologies there? What is it about the UK? First thing is that we have one of the tightest regulatory regimes. So if you can pass through the UK regulator, there's every chance that you can get your license, your technology licensed elsewhere. But the other thing is this: it's market reform. So the UK has decided to do things in a slightly different way in terms of a market correction. You will know that the real challenge in bringing technologies to market, which costs so much, as we heard, who's going to put up the money if you cannot be guaranteed a return on that investment? So through the electricity market reform in the UK, we have a new instrument which is called contracts for difference. Contracts for difference is, in this particular case, the government agrees with, in this case, EDF, we will pay you 92.5 pence per megawatt hour for 35 years. So it's a contract which lasts 35 years. And then the company knows that they can make their money back. And the way it works is that you agree a strike price, which is at 92.5 pence. If the market price is less than the strike price, then the consumer has to top that up. So there's some money which has to come from the consumer and gets handed over to EDF. Vice versa, if the market price is higher than the strike price, then actually the consumer benefits. That will never happen. And the company gets a strike price. So that's the thing which has incentivized all of these companies to come and try their luck in the UK, because we've got this new market instrument. What are we doing in the future? So we heard about fuel cycle and things like that. And at the moment, the UK is in an open cycle. So uranium is mined. And in the UK, we can do the enrichment, Urenco, we can do the fuel fabrication. We've got a few reactors. And then the fuel, after that, goes into storage ponds. We, until very recently, had a reprocessing capability. So what that means is that you can take the fuel, reprocess it, and extract the uranium and put that back in the fuel cycle. Of course, what that means is you create plutonium. We have a plutonium stockpile, and we have a vitrification plant, and we have a MOX plant, which means that you can use that plutonium in MOX fuel. We had a MOX plant. We are working our way towards a waste repository. So by 2040, we will have a waste repository that, again, is mandated, so deep geological disposal. And maybe one day we have an integrated system with fast reactors. Very finally, I'll just tell you what is exciting people no end in the UK at the moment. People being the government, and they've put a quarter of £1 billion into this initiative. In this sense, we're trying to catch the US up. Because the UK doesn't do large-scale reactors anymore, well, maybe we could do small-scale reactors. So there's a lot of effort and thought going into developing small modular reactors. Advantage being, the first one is cheaper, so it doesn't cost 18 billion, and you use the funding from the first one to fund the second generation or the third generation, so it softens the pain, financial pain. SMRs have greater load following capability, so they're much more flexible. In principle, the efficiency and safety is higher. You can use higher enrichment fuels in SMRs. And you can extract the waste heat. So actually, we are looking at combining technologies that extracts that waste heat, energy storage technologies, with an SMR reactor, which can give a reactor dynamic range from 90 megawatts up to a gigawatt. So actually very, very flexible. And the last thing is the UK, we build small reactors. We have a company, you may have heard of them, called Rolls-Royce. And they build the nuclear reactors which go in our fleet of nuclear submarines. So at least we can build a nuclear reactor which is small, and we just have to go from a military one to a commercial one. So that's what's happening at the moment. Anyway, I will stop there. Again, thank you for a very stimulating conference, and I've left you with my thoughts. Thank you.
So, good morning. I'm Jim Stubbins. As you can, well, not as you can see yet. Yes, as you can see, I'm a faculty member in the Department of Nuclear Plasma and Radiological Engineering here. And I also want to acknowledge that we do have some funding from National Science Foundation to look at nuclear policy related things. And I have a very strange title, and I promise you there will be no singing in this presentation. But I use the title to make a point that is kind of in the subtitle of what's there. And that is that, as we saw from all of the other talks, nuclear power has a place. The question is, how big a place should it really have? And you heard from Professor Uddin that there is a good set of arguments for it taking a bigger place. And this is the thing I want to talk to you about. So many of you have seen this slide. I think this is kind of a universal slide that shows from the U.S. Energy Information Administration what the energy sources in the U.S. are and where they go. And of course, if you look at this slide on the very bottom level, you'll see nuclear power, and you'll see that 100% of it goes to electricity generation, which accounts, and this is the most recent one from 2015, goes to about 22% of the electric power that's produced is nuclear generated power here. You can look at all the rest of them. Of course, the other major message here is that if you look at the very large petroleum, natural gas, and coal part, the fossil fuels, that's 85% or so of the total energy generation in the U.S. So this is a very large fraction. The other, I think, message, there are lots of things you can extract from this slide, but the other message is that if you look at nuclear energy, it doesn't impact many of the other areas where it's I think, sorely needed in terms of having some impact, particularly on transportation and industrial things. And this is the thing I want to talk about. The other thing to note is that, and I'll show you this slide. This is one from 2005, same kind of figure. The difference, if you compare them, is that natural gas has grown substantially in its impact, particularly on the electric power industry. The electric power industry was half fueled by coal, even as little as 5 years ago or so. And now natural gas has taken a much larger fraction of the electric power industry, among other things. Renewables also, if you compare this from 2005 to 2015, have grown somewhat over that period of time, and we'll look at that as well. And so here's a projection from the Department of Energy Information Administration. This is also from their Energy Outlook, which is supposed to come out this month, but there are some previews of certain areas. Thing to note here, a couple things to note here is, again, that natural gas, petroleum, and coal make up the largest fraction of the energy sources, and this is projected out to 2040. Okay, so we're looking at 2030 here primarily, but you can see that there's not much change there. Renewables actually increased somewhat. The other thing you'll note from this chart is that it does include so the reference case is with the Clean Power Plan, which would move away from at least the worst part of carbon emissions. So you'll notice it in the reference case, which when you look at this is on your left, the coal amount has decreased because this is actually what's the biggest impact of reducing carbon emissions, whereas the other places basically take up for this. If you look at the world instead of the US, I don't have a nice stacked diagram here, but if you look at the International Energy Agency view, you'll see again liquid fuels and natural gas play the largest part of the energy world supply. Coal is flat over the next several years, and renewables have an increasing impact. Though they grow quickly, they don't grow as quickly as natural gas in these projections. Also, as you heard, I think from Martin's talk, that nuclear is growing worldwide. It's not growing so much in the US, but it's growing worldwide, so this will have some impact. But it's still a minor part of whatever's going on there. If you look at the carbon emissions, and so to remind you, coal is the worst of the carbon-emitting fuels. There's a chart here, again, from the US DOE Energy Information Administration. You'll see that natural gas is roughly half of what coal emits, and a lot of what's in the Clean Power Plan, this CPP thing, is basically switching from coal to natural gas. Nuclear has a very minor impact on that. If you look worldwide at emissions, again from the International Energy Agency, you'll see that the biggest impacts here, again, liquid fuel, natural gas is rising, but coal is also a very major international impact on carbon releases. If you look at electricity themselves, I won't bore you with going through all of these again, but you see that if you have a clean power plant in the US, this is US information, the use of coal would be roughly broken down to maybe a third or at least less than half of what it was previously, but this is made up by lots more use of natural gas and some expansion of renewables. If you look at the other things on the bottom, nuclear stays relatively similar. If you look worldwide, same thing. Natural gas increases. You can see the increases projection here. Renewables increase projected. Coal roughly flat in this, and you do see the impact of increased international nuclear for electricity generation. So the point I want to make is this. When I came here in 1980. So 36, 37 years ago. I came here from General Electric where we were working on high temperature gas-cooled reactors. So one of Hans's favorite technologies. And in those days, so this is 36, 37 years ago, the effort was, there were three major worldwide efforts. One was in the US. This was to develop a very high temperature gas-cooled reactor, so not water-cooled. These are very large systems. The energy density isn't very high. They don't contain a lot of energy that can be released, though the gas is under pressure. But if you can heat gas to very high temperature, these were cooled with helium, you can then use the helium to run a gas turbine, so like a jet engine instead of jet fuel, or a gas turbine, a ground-based gas turbine. And the heating source would be the reactor, not some combustion process. And this would produce electricity. But the other things that we were doing, and the other places I'll mention in a minute were doing, is trying to develop a very high temperature heat source for doing other kinds of things, for thermochemical processing. Germany had also a very major program in this area. They were only interested in nuclear process heat. They didn't want to make electricity. And what they wanted to do is change their brown coal primarily into liquid or gaseous form for fuel processes. So this would have a big impact. So I put this up here inside the middle of this chart. So these things would have a big impact on the transportation industry, the transportation sector and the industry sector, not directly on the electricity sector. Japan was doing the same thing. Japan was very interested in developing these high temperature gas-cooled reactors for steel refining, to pull the oxygen off of the iron in iron ore. So this is 36 years ago, and you just saw from the chart that all of the nuclear power in the US goes for electricity generation. We haven't made any real impact in here, which could have a major impact on these two sectors where there is a huge amount of fossil fuel consumed. Remember, transportation is almost exclusively petroleum. Okay, there are some changes now. And we know now that there's a possibility of using battery electric vehicles. I'll say something about that in a minute. Where transportation could be impacted by the electricity generation part, there are other possibilities as well. Where did these programs go? So this one evaporated, but came back maybe 10 or so, 15 years ago. But we're still not at the point where we're doing this. The Germans had a nice reactor here. It's now in China. It now belongs to Tsinghua University in Beijing. And the Japanese actually, typical of the Japanese efforts, which always move forward, have produced a high temperature test reactor, HTTR, which has reached an outlet temperature of 950 C, which was the target in those days. To get to reasonably high temperatures like 900 to 1000 C, you can actually do thermochemical processing and replace a lot of fuel sources that would otherwise be fossil sources. So why isn't the US doing more of this, or why isn't the world doing more of this? This is, again, Energy and Information Administration slide showing two things, showing the growth. So this is the growth rate of electricity in the US starting back in the 1950s and GDP. What you note is that there was very high but very non-predictable growth rates of electricity use starting in the 50s, but at least for projections, this growth rate, which is now much smaller, less than 2% per year, looks to be like it could be much more predictable. This is, I think, one of the major factors for the US not pursuing nuclear in a much greater amount to meet these demands which are otherwise met by fossil fuels. And as you've heard from the other talks, the major drivers are the cost in energy supply. In certain sectors, particularly now in the renewable sectors, there are financial incentives, though nuclear has some financial incentives, some loan guarantees. Construction time is a major factor in trying to change the policy for having nuclear taking a bigger part in the energy portfolio in the US. And this is because it takes 4 or 5 years. In some older plants, you know, these constructions times extended for 14, 15, 16 years, so very long periods of time. And that makes things very unpredictable. So this is a major issue. This is much easier to do if you're putting up a wind turbine in a few months than building a nuclear plant, which is going to take 4 years. And you heard also the regulatory issues here are similar to the ones in the UK in terms of getting things built and approved and operational. And finally, there's the financial risk. If you look at the ups and downs here, you can imagine if you make a decision and go through any four-year period here, there's a lot of change in the way the electricity growth goes. So what has happened in the US? Here's a figure that shows the generating capacity additions. So these are additions to what particularly electricity generation have been in the US. So for those who can't see the color coding on this, you notice that the nuclear and the coal parts are here, some coal in here and a little bit of nuclear here. Primarily, this is natural gas oil, starting in the early 90s, but really increasing in terms of generation capacity around 2000. And some increase in wind and solar. So wind is green here, solar is yellow. You can see those increases again started in the mid-2000s. And if you look at the projections beyond this year, so this again is information which was released this May, so it's relatively recent. You notice that there are two major parts here, natural gas, oil, and solar. So this also has some reflection on policy because part of the reason the green part, the wind part, dies out in 2020 or 22 or so is due to the fact that the production tax incentives are scheduled to decrease to zero by then, though they're still in force now. But they will decrease gradually over the next several years. And so these are policy issues that dictate what kind of, so the uncertainty in the market and the policy issues that are either incentivizing or de-incentivizing these kinds of decisions about what to install in terms of generating capacity have really made a big difference in the US. And so I think the lesson here is that short-term, low-risk decisions are the best kind of decisions. This is not consistent with doing better in terms of energy reliability or other issues that have to do with the environment. This is a similar chart that shows generation additions in the next 4 years to 2030 to 2040, based with the Clean Power Plan or without the Clean Power Plan. You notice that the bottom line is what gets taken out and the top line is what gets put in. In this case, nuclear is fairly neutral. There are nuclear plants taken out, but there are also nuclear plants that will start. But you notice that coal is largely gone here. We heard this about the UK as well. And the major inclusions here, you can see wind still has some impact in this time period, but after 2020, no more wind, almost all solar, and natural gas. So this is a question, I think, about what the energy planning should be for the future. So The forecast, so I said this, so I'm not going to dwell on this again, but there's a very heavy reliance on continuing using fossil fuels. This has some issues. Even though carbon's diminished, there are still a big carbon footprint from the rest of the use of these fuels. Increased solar over this period, but relatively static wind after the next 4 or 5 years, static nuclear, and little penetration of these technologies into the transportation sector, particularly where there's lots of liquids. I also wanted to just note that if you go around the country, the type of generation, and this is a point that I'll make again in a second, depends a lot on where you are in the country. So when I worked at GE, I lived in Schenectady here, and if you look at the power generation mix in Schenectady, even now, here's the key down here, no coal. Okay, when I lived there, there was no coal. There was actually not much natural gas. Now there are natural gas lines there. So people burned oil. This is because coal's not very clean, and the area where I lived was very heavily impacted by acid rain issues. And if you look at other places, you can see that the north central part of the country has very heavy reliance on coal. And you can look at the mix other places. In matter of fact, if you look at the mix of things that have to do with renewables, you can see very heavy renewables in the Northwest, which we would expect. And in some other areas of the country, there are relatively big impacts, particularly solar areas. California has a plan to get to 33% in the next few years. But if you look at in the Southeast, renewables are still a minor part of what can be done there. And even in the north central part, you see renewable. This is primarily wind. And the reason I make this point is I wanted to show you the impact of this is a story that again showed up on PBS NewsHour in May about the impact of using gasoline-fueled vehicles versus plug-in vehicles, so battery electric vehicles. And the presumption is that you're charging these at night. And the argument is that if you charge these at night, primarily you're using fossil fuels, so base load power, which is primarily coal, and you're actually, even though you have a plug-in electric vehicle, if you're charging these overnight, you're actually emitting higher, because the plug-in electric vehicle, you're emitting higher amounts of carbon. And this is because charging happens at night. This is not Elon Musk. This is Thomas Edison, and this is a battery electric vehicle from 1911. And this looks at Toyota Prius, both the hybrid version and the plug-in version. You can see that when you compare the two, there's not much different. But if you compare to the Chevy Volt, for instance, with the Prius gasoline hybrid, you can see there's a lot of impact of higher emissions if you're charging at night using primarily coal. So I think this is a big issue. Base load, so part of my message is I think nuclear should take a bigger share of the base load power. This would actually move things very much in this direction because as you saw from the other talks, there's not the same kind of base emissions associated with this. It also argues that there will be not these big up and downs that you saw in Martin's talk, for instance, about daytime use and nighttime use, because there will be, I think, a lot of shift in the market for using these kinds of things. So my feeling is that nuclear should play a bigger part. Certainly, it can do a lot more in the base load market from battery electric vehicles or plug-in vehicles. I'll show you something about server farms, energy storage. Hydrogen is another major thing. And if these things can happen, there would be a major penetration into these sectors here, particularly, rather than just nuclear playing a major role in the electricity part, which it's actually 20% is not a major role. And here's where the title comes from. This is a picture of the Poseidon, actually Carlsbad. This is named after a person, but Carlsbad, which is near San Diego. It produces 50 million gallons per day of purified water, takes in 100 million and releases the other 50 million. It works continuously, 40 megawatts continuous power. It's about 10% of the San Diego water supply system. This was turned on last December, so December 5th, 2015. This is a base load kind of application. And just up the coast from this particular water treatment plant, So there was a huge amount of effort put into getting the environmental approval for doing this. Are the San Onofre nuclear generating stations, SONGs, which actually only operated from 1984 to 2013. So there was a unit 1 there. This shows you units 2 and 3. These are about 1,000 megawatts electric each. So this kind of baseload power, which would have avoided any of the kind of other releases that are required to run these kinds of plants, shut down. So this power is gone. So clean power, as you saw from the other talks, to run these kinds of things. I mean, there's other controversies about how the water is released, how the salinated water that's higher salt contents released, and other kinds of things. But the issue about doing base load power things, which is actually increasing quite a bit now, I think nuclear can play a huge role in that. Capacity factors, this is another International Energy Agency figure. This shows capacity factors. Hans talked about capacity factors. Nuclear does very well in capacity factors. So if we're looking at base load, here's the US, here's many other countries in the world, but you notice that nuclear is on almost all the time, whereas solar, wind aren't. Hydros depends a lot on what you have and where it is. Petroleum, natural gas are on and off. This is, again, a lot to do with peak loading. And you can see coal here actually doesn't have the same record as nuclear. So going back to a stronger base in terms of base load power, which also would help levelize what's going on day and night, nuclear plays a great part. Data centers, another thing that are on all the time. And if you look at how many in the US, what data centers there are, 91 billion kilowatt hours per year. This is essentially the equivalent of about 17 nuclear power plants. The projection by 2020 is to go to 140 billion, though some people think this is going to level off. This is something like 25 nuclear power plants, or twice that many coal power plants. These things are on all the time. These are baseload stations. If you look at the industrial sector, where nuclear has had very little impact, you can see that. So this is a breakdown of these various things. Here's electricity, and this is actually just natural gas. You can see where the fraction of the natural gas uses in electric power generation. You notice that there's a much larger fraction in industry. And so this is process heat. This is where I came here from GE to look at this. Nuclear can play a major role in this as well, as long as we develop the technology that will give nuclear process heat. And as you saw 37, 38, 39, 40 years ago, this was a major effort around the world, and we just haven't gotten there. And I should note that 2030 is a lot closer to now than 1980 is to now. So we have a lot to do. The other thing is, I just want to make the point about fuel prices. This, again, is a projection. Gasoline or liquid fuels so this is Brent crude spot prices. This is where things have been the last few years. Here we are now, and here's the projections. This again is the Energy Information Administration projections. Here's natural gas, Henry Hub spot price. You notice this ratio is small now, but if you go ahead to 2030, 2040, this ratio is huge. This means that there needs to be some shift off of, even though we can produce more liquid fuels in the US, we can be self-dependent in this area now with fracking, but this is another huge opportunity for switching to other kinds of transportation modes, which could rely much more on non-polluting, non-emitting nuclear power sources. Okay, and this is the last slide. This is a scheme from Chauncey Starr, who was the chair, or whatever, the head of EPRI, and Paul Michael Grant this is more than 10 years ago, so maybe 15 years ago. This is a scheme where you take nuclear and make hydrogen from this. The hydrogen could feed a number of entities, home, school, supermarket, here's even DNA testing. The other thing, though, is that liquefied hydrogen could be transported, and you could also cool superconducting transmission cables. This would vastly change energy loss. Also, when I worked at GE, we were working on a big superconducting energy transmission system that would run down the Atlantic coast. Okay, that's again 40 years ago. And if you can do this, you can also use magnetic levitated vehicles. This also is very high-speed technology. And so this kind of picture is basically shows you where nuclear could go in the future. I think can have a huge impact on all of the other energy sectors where there are major emissions. I think that the amount of cost of power you saw from these, if you take particularly emissions into account, nuclear is really competitive in this area. We need a policy where we're going to get there. Thank you.
Let me thank the speakers for not only interesting talks, but talks that were all on time, which is great. And so we have some time for questions. And there's one over here.
Thank you. As demand for building nuclear plants continues to be dominated by China, how do you expect that China is going to, or sort of in response to that demand, that's going to alter the path for innovation related to nuclear energy?
I'll take a stab at that. China is, a very superficial comment looks very similar to what the U.S. looked like and the UK looked like about 50 years ago in terms of experimentation, trying different things. They've got a molten salt cooled reactor experiment they're developing at the University of Shanghai. In 2017, a high-temperature gas-cooled pebble bed reactor is scheduled to come online, the first commercial unit. And of course, they've got an experimental sodium-cooled fast reactor. So yes, they're building, certainly building light water reactors, Gen 3 designs at a great rate, but they're also looking at other things too. As we see in other areas, China is coming on strong. They're very innovative. You can compare the regulatory and financial environments for those things and draw your own conclusions. I'm not an expert in those areas, but one can expect to see a lot of innovation out of China and Korea as well. A lot of the innovation is coming out of the Asian countries these days, and it'll be interesting to see if how soon it will be before the U.S. buys a nuclear power plant from China.
So the other thing to mention is that China's not just doing innovation, but they're thinking about the fuel cycle. So they're not just interested in reactor technology. And you will notice, if you follow the news, that Chinese companies are buying up uranium mines. They're also investing in, at the moment, French reprocessing plant. So my suspicion is that the longer-term plan is to own the whole fuel cycle. So own reactor technology, including fast reactors, sell you the fuel, sell you the reactor technology, reprocess the fuel for you. So I think they have thought through what a long-term investment plan looks like in terms of nuclear. And of course they need to do this because they're building several hundred nuclear power stations in China. And so they need to maintain that sustainability, but also having done that, they can control the world market.
I might add that I think there are two parts to the question, because one of the issues is if China wants to sell reactors other places in the world, as you heard from Martin, they need to meet the regulatory requirements in those countries. And I think that's a major part of their plan right now. The other half, though, is how innovative they're going to be. And as I told you, the gas-cooled reactor technology developed in Germany was transported there. They have they have been much more open about trying to look at other kind of nuclear facilities configurations than anywhere else in the world. They're behind where the rest of the world is, but they're on their way to doing a lot more.
Great. Thank you very much for a fascinating panel. I learned a great deal. I'm an economist. I'll be a little provocative. This was a very bullish panel on nuclear. I want to bring up the question of cost, and really there are two components to this that I want to ask, and this is for anyone on the panel. One is looking at recent history, and even going back a great deal, there have just been cost overruns time and time and time again when you look at nuclear plants, and this has made both investors as well as the U.S. government at least a little uncomfortable about diving into nuclear the way that several of you have suggested. And the second is disposal of waste. I believe waste can be disposed of in a safe way, but it's not going to be cheap, and everyone knows that. And in the United States, we don't yet have a single place. As we know, Nevada, Yucca Mountain is not a viable option at this time for political reasons. And maybe this is a question part for the UK example. I was looking online while you were talking, and it doesn't look like you've nailed it down in the UK either fully, although that could be different. And so that's another huge cost. Is that incorporated in your considerations of how to think about nuclear going forward as well?
So I'll have first bash from a UK perspective, and then I'll hand over. So cost overruns. So there is some, it's called nuclear inflation, isn't it? And it's about 6%. So if you average over, at least in a UK perspective, the history of nuclear build, one has to look towards what's happening in China. So in China at the moment, by and large, their plants are to time and to budget. So the Taishan plants, for example. So what is it we can learn from the way that Chinese have managed to, maybe if there's things you cannot translate, so working practice in China may not translate, for example, into the US or the UK. But in terms of project management, they have done some fantastically good things that the rest of the world can learn from. Modular construction as well. So if one looks at the ABWR, that's as a modular construction. It means that it has been built many times. It's built in a factory, and you assemble those components, and that's a more reliable, simpler construction process. So there are, I believe that things are heading in the right direction. But take any project, if it overruns substantially in either time or budget, that's the end of the nuclear program for at least in the UK. Public opinion would fall away. Waste. Now, to put a scale on the waste problem in the UK, it's so we have somewhere called Sellafield. It is the reprocessing plant. It has a big history in terms of military and civil. It's £100 billion to decommission the Sellafield site. 100 billion. And that is just integrating over all of the activity that we have, nuclear activity that we've been doing in the UK over those 50, 60 years now. Now, to put that into perspective, if we were to operate a fleet of nuclear power stations into the future, conventional or fast reactors, that will only add 10% to that legacy problem. So in fact, we've got to deal with the waste whatever. So we need a waste repository. You're right, the internet in this case is right, that we haven't completely nailed that down in the UK. We're on a journey. It's an interesting journey where we're trying to learn what has been done in Scandinavia in terms of how you bring the public along with that. Anyway.
We have two more questions and then we're out of time. So brief answers, please.
I was really quite interested in benefit cost analysis. Is there a procedure to assess water quality, principles and guidelines? Oh, okay. There are procedures to assess a lot of federal projects called principles and guidelines. So I think that you can develop a benefit cost analysis for nuclear and climate change, because I think stuff like this is really, really important. But one type of thing that is really amazing is everything here has some military application. If China is dominant in terms of nuclear technology, it it will have dominance in a lot of other things. Then the US thinks, okay, let's have, there is a lot of danger in nuclear. It's perceived very dangerous, but there is also an element that if you know about the technology, it gives you some sort of an edge. So when you do benefit cost analysis, my main worry about nuclear is that someone would use a nuclear power like what happened in Holland and smuggle it off to Pakistan. That's what really happened. And the same way, if you don't have capability in nuclear, you are aware, you are behind militarily. Does anyone think about it? Because to me, that's the main issue of nuclear. Not everything else is really minor.
I think it's a very important point. I mean, non-proliferation is at this point, at least in the government circles, is one of the most important concerns, and that is part of the reason why, in some ways, if you look at the budget allocations from the Department of Energy and Department of Defense and the programs under NNSA and other, there is significant amount of money actually that is going towards non-proliferation efforts to make sure that we are on top of things and we know where the technology is going, and if we can have detection capabilities so that the technology does not spread. But in answer to the previous question, I think that boat has already gone as far as China's leading the effort in the nuclear business is concerned. China is way ahead of every other country currently. All the Gen 4 reactors that you saw, that we are still debating whether they are going to happen, what needs to be done to make the first prototype, at least 2 or 3 of them are already being constructed or operating. The VHDR is there, the fast reactor, that no other country has. So I think the policy or the perception will have to change now, that U.S. at least is already behind China in terms of technology implementation.
I would just like to ask if you, I don't know, Martin or Hans, can give us a little bit more information about the waste product and the potential for capturing energy. It sounds like, Martin, in the UK, that's sort of being shut down. I understand it's expensive, but it also sounds like, building Generation 4 is expensive too. So why isn't there more interest in trying to recycle the waste product?
It is in the end down to whether it's commercially viable or not. So although from a national interest perspective, one might like to have a closed fuel cycle and do reprocessing and construct MOX fuel, the way the markets operate, or the way the government operates, is that it's all market driven, and unless the price point is right, you will not have reprocessing and utilization of the second use of fuel. So maybe at some point in the future, when uranium reserves begin to peter out, and that people have to look a little bit more hard at reactor technologies and fast reactors, but we're not close to that at the moment.
I'll just briefly agree with that point and expand on a different direction. Yeah, the recycling is not a cheap technology. It's a very chemically intense process to separate things out, and of course there are radiological concerns, worker safety and all that. Oh, thank you. There are a few plants around the reprocessing plants around the world, the Sellafield being a major one in France and Japan, and we used to have them here and don't anymore because for various reasons I won't go into. But some studies, there was one study at MIT I just read recently that indicates that in order for recycling of nuclear fuel in a fast reactor or even in thermal reactors, to be competitive with the once through, dig it out of the ground, enrich it, and put it in a light water reactor, the price of uranium from the mine would have to increase by a factor of 5 before it becomes competitive. So it's not, recycling in this case is not a freebie. It's very doable. Look at economically attractive if uranium resources become scarce, or if the cost of disposal of spent fuel becomes prohibitive. And first of all, uranium resources are not scarce. Well, as in the slide I tried to indicate, they'll be around for a long, long time, and we haven't even looked everywhere yet. And then as regard to the waste, the cost of containing the spent fuel, getting to your question, on site, not an optimal solution by any stretch, but containing 40 years or 60 years of waste on site through casks and qualified containers is barely factors into the costs of the life cycle of the plant from a utility standpoint. So I question the premise of your point that it's a very expensive issue. Waste is not. It's one of the highlights of the nuclear power industry that we can store all of our high-level waste in small containers safely, indefinitely, for fairly minimal cost. Nor would I think that deep geologic disposal, which is also expensive, at least when you do it the way our federal government tries to do it, is an optimal solution either, because then you're just throwing away 90% of the energy content of the fuel that can't be touched again. I'm in favor of some more monitored retrievable storage or options like that, but nonetheless, it comes down to a cost issue, as Dr. Fear suggested, that the economics are just not there yet.